Today we are discussing about differentiation. What is differentiation? That is what is derivative. That is what is the rate of change of function. For this we are taking an example. The example is like this. Suppose a particle performs motion in a straight line. The position of a particle is given by x of t equal to 4.21 t square plus 2.60 meter. And we are raising two questions. A. Find the average speed of the particle in initial 3 seconds. B. Find the instantaneous speed of the particle at t equal to 3 seconds. First question is average speed in initial 3 seconds, and we know that average speed, here the particle is performing motion in a straight line and it is not taking U-turn. So average speed or average velocity is equal for this example. So average velocity is change in position, that is displacement, upon time taken. And we want to find the average velocity between t equal to 0 to t equal to 3. So x of 3 is final position minus x of 0 is initial position upon 3 minus 0. What about x of 3? So if we put t equal to 3 in this formula, we get final position. So after calculation, it is 40.49. And what about initial position? If we put t equal to 0, we get initial position, which is 2.60 by 3. So finally 12.63 meter per second. It is the average velocity in initial 3 seconds. Now important question is, find instantaneous speed or velocity of the particle at t equal to 3. For this, we are taking smaller and smaller time interval around t equal to 3. So first we will take time interval of 1 second after 3. So x of 4 minus x of 3 by 1. X of 4 represents position of the particle at t equal to 4 seconds, and x of 3 is the position of the particle at t equal to 3. And time interval is 1 second, but x of 4 is what? So if we put t equal to 4, 4.21 into 4 square plus 2.60, we get 69.96 after calculation. X of 3 well defined 40.49. So this is the final initial position, this is final position. Time interval is 1 second. So the final answer is 29.47 meter per second. It is the average velocity of the particle in a time interval of 1 second after 3. That is, this is the average velocity of the particle in 4th second. But we want to find instantaneous velocity of the particle at t equal to 3. So in second case, we are taking smaller time interval. See here, x of 3.5 minus x of 3 upon time interval is half second. So this time we are taking time interval of half second after t equal to 3. So x of 3.5, after calculation we get 54.1725 minus 40.49 upon half. So 13.6825 upon 1 by 2. So finally the answer is 27.365 meter per second. It is the average velocity of the particle in a time interval of half second after 3. Then after, we are taking more smaller time interval. X of 3.25 final position, x of 3 initial position. The time interval is 3.25 minus 3, it is 1 by 4. If we put 3.25 in the original equation, we get final position as 47.068125 minus 40.49 upon 1 by 4. So finally we get this result 26.3125 meter per second. This is the average velocity of the particle in a time interval of 1 by 4 second after 3. but we want to find instantaneous velocity of the particle at t equal to 3. So this time we are taking more smaller time interval. X of 3.1 minus x of 3 by time interval 1 by 10 second, 3.1 minus 3. So time interval is 1 by 10 second. X of 3.1, if we place here, we will get 43.0581 minus 40.49 divided by 1 by 10. So finally we get this answer, 25.681 meter per second. But this is also the average velocity of the particle in a time interval of 1 by 10 second after 3. In last reading, we are taking more smaller time interval, 1 by 100 second. So x of 3.01 minus x of 3 by 1 by 100. So after necessary calculation, we get 25.3021 meter per second. See here, after 1 second, average velocity 29.47. After 3, in half second, average velocity is 27.6365. After 3, in 1/4 second, average velocity is this. After 3, in 1 by 10 second, average velocity is 25.681. And after 3, in 1 by 100 second, it's very small time interval. The average velocity is 25.3021 meter per second. But this is not exact velocity we want to find. We want to find instantaneous velocity at t equal to 3. But this way, we can't find exact velocity. Because if we take smaller and smaller time interval, we are going towards the right answer, but we will not get it. So we have to make trick. This time we will not put delta t, very small, but we will imagine if it takes very small time interval delta t, the expression, the ratio, displacement and time goes to which number? So in general, suppose we want to find instantaneous velocity of the particle at any instant t. So delta x is change in position, which is called displacement. Delta t is time interval. So this represents average velocity. But if we consider, if we apply this condition, limit delta t tends to 0, we will get instant velocity. That means if we take smaller time interval, smaller and smaller time, if we imagine the ratio of delta x by delta t goes to which number, and this represents exact velocity. So limit delta t tends to 0, x of t plus delta t minus x of t upon delta t. According to the formula, limit delta t tends to 0, 4.21 into t plus delta t whole square plus 2.60 minus 4.21 t square plus 2.60 upon delta t. So v equal to limit delta t tends to 0. Expanding this, 4.21 into t square plus 2t delta t plus delta t square plus 2.60 minus 4.21 t square minus 2.60. These two are cut out. Multiplying, limit delta t tends to 0, so 4.21 t square plus 8.42 t delta t plus 4.21 delta t square minus 4.21 t square. This one cut out. Now we have three terms, this and this. So as delta t tends to 0, delta t is variable quantity, this term should be going towards 0. This term is also going towards 0. So numerator is going towards 0 as a whole because t is constant. Denominator is also going towards 0. So we have a fraction. Its numerator is going towards 0 and denominator is also going towards 0. And we want to find this expression is going towards which number. So according to our common sense, it is going towards 0, it is also going towards 0. It may be 1 or infinite. But this common sense is not right. For example, consider this illustration. Limit x tends to 2. We will consider this example. Limit x tends to 2, x square minus 4 upon x minus 2. As x tends to 2, this number is going towards 0 and this one is also. But as a whole, the value of expression, this ratio, is not going towards 0, is not going towards infinity. It is going towards 4. If you take x equal to 2.1, 2.1 square minus 4 upon 2.1 minus 2. So 4.41 minus 4, 2.1 minus 2. So 0.41 upon 0.1. So 4.1. If you take more close value, 2.01. So 2.01 whole square minus 4 upon 2.01 minus 2. So 0.0401 upon 0.01. So 4.01. The observation is that it is going towards 4, not 0. Even then, numerator goes to going towards 0 and denominator also going towards 0. But the value of expression going toward 4. We can treat like this. Limit x tends to, if you factorize this, x minus 2, x plus 2, x minus 2, a cut out. So limit x tends to x plus 2. The answer is 4. As x tends to 2, x plus 2 is going towards 4. This trick here, if you take common delta t here, so taking common delta t, we get 8.42t plus 4.21 delta t upon delta t. So cut out. Now it's a constant term. If you consider t is constant, this term is going towards 0. So as a whole, as limit delta t tends to 0, this term is going towards 8.42t. And this represents the instantaneous velocity of the particle at any instant t. Now we are taking some more example. Y equal to f of x equal to x. So dy by dx equal to limit delta x tends to 0, delta y by delta x. So limit delta x tends to 0, f of x plus delta x minus f of x upon delta x. This is the common formula for differentiation of any function. But here f of x is x. So f of x plus delta x is x plus delta x minus x delta x. This cut out, delta x by delta x is 1, it's constant. So limit delta x tends to 0, 1 is 1. So dy by dx is 1. But what is y? So y is x. So d dx of x is 1. Second example, y equal to f of x equal to x square. So dy by dx, so limit delta x tends to 0, delta y by delta x. So limit delta x tends to 0, f of x plus delta x minus f of x upon delta x. This term is a common rule. For any function, it represents rate of change of function. So limit delta x tends to 0. Here f of x is x square. So f of x plus delta x is x plus delta x whole square minus x square upon delta x equal to limit delta x tends to 0, x square plus 2x delta x plus delta x square minus x square upon delta x. Cut out. After taking common, we get 2x plus delta x. Delta x cut out. So this term is constant because we are considering x constant. Delta x variable quantity. As delta x tends to 0, it is going towards x. So dy by dx is 2x. But what is y? Y is x square. So d dx of x square is 2x. Similarly, y equal to f of x equal to x cube. Now we are taking x cube. So dy by dx is limit delta x tends to 0, delta y by delta x equal to limit delta x tends to 0, f of x plus delta x minus f of x upon delta x. But this time f of x is x cube. So limit delta x tends to 0, x plus delta x whole cube minus x cube upon delta x equal to limit delta x tends to 0, expansion x cube plus 3x square delta x plus 3x delta x square plus delta x minus x cube. This will cut out. Now taking common delta x, 3x square plus 3x delta x plus delta x square, delta x cut out. So as delta x tends to 0, this term is going towards 0, this term is going towards 0, it's constant. So as a whole, this expression going towards 3x square. So dy by dx is 3x square, but what is y? Y is x cube. So d dx of x is 3x square. So after logic, d dx of x raised to 4 should be 4x cube. Similarly, d dx of x raised to n should be nx raised to n minus 1. That's it.